Good morning, guys. Today we will be looking into kernel symbols. So what is a symbol? A symbol is either a variable or function. It is a name which is representing a space in memory which stores data, which can be a variable like for reading and writing, or it's a stores instructions or functions for executing. So kernel symbol is nothing but it's either a name of a variable or its name of a function. So these symbols, they are visible at three different levels in the kernel source code. First one is static. When you have a static symbol, this means it is visible only within their own source file. If you have an external symbol, it is visible to any other code which is built into the kernel. If it is exported, it is visible and available to all loadable modules. So kernel code, it can make a symbol available to loadable modules with export underscore symbol and export underscore symbol underscore GPL macros. This we have already seen. And we already know about kernel symbol table. The first symbol table is present in system.map. It contains all the symbols which are exported by code which is built into the kernel. Then we have proc call symbs. It contains system.map symbols plus the symbols which are added by the loadable kernel modules. So we have already known much of the information which is present in this file. So conclusion is symbols is nothing but it's a name of a variable or function. There are three different levels. One is static, one is external, one is symbols which are exported. So question is, how do you find out whether a function is static or global by looking into proc call symbs? So you have proc call symbs, you have a function, and you want to find out whether this function is static or whether this function is global. How do you find out? So let's look into the answer for this. So grep for the function which you want to look. Suppose if I want to look for a function msleep, I want to find out whether this function is static or global. If you see small t, this means it is static. If you see capital T, it means it is global. So proc call symbs, they follow nm syntax. So nm is a tool which displays all the symbols which are present in an object file. So proc call symbs, they follow nm syntax. So now if I want to find out whether the symbol is static or global, I can look into T. If it is small t, it is static. If it is capital T, it is global. So proc call symbs grep msleep. I see it is capital T, so this means it is a global symbol. And if all the exported symbols, they also have another symbol prefixed with underscore underscore kSymTab. So you can see here for msleep we have another symbol which is R, which is prefixed with kSymTab. This means the symbol is exported and it can be used by loadable modules. So capital T means it is a global symbol, and whether this global symbol is exported or not, you can verify by if it has an entry underscore underscore which is prefixed with underscore underscore kSymTab. So all modules, they have their own symbol. Yes, symbols are nothing but names of variables or functions. Suppose I have a module hello.ko which has lot of functions, variables and so on. I can look into the symbols by running nm on the ko file. So after compiling the module, we have the ko. We can get a list of symbols by running nm on the ko file. If you see u, as a symbol. We have seen T and small t and capital D, which is for text segment. U means it is undefined. So let's see, we have a simple module. I have a global variable here. I have a static variable here, which is a global static variable. And then I have a function which increments the static variable. I have a function which increments the global variable. Then I have a local variable. I'm calling the static function and global function from this init function. So now we have to think whether all this will be present in the symbol table. We know we can we can check the symbol table by using nm command. If I give nm command on the KO file, it will give all the symbols that are present in the KO file. So, and we also know that symbols is nothing but a name of a variable or function. So now question is, will we have all the variables, like whether we'll have global variable in symbol table, whether we'll be having static variable in symbol table, whether we'll be having static function, global function, whether we'll be having local variable in the symbol table or not. So let's verify whether what all are being added in the symbol table. So let's go to clean and make. So now let's run nm on hello.ko. So we see here we have cleanup underscore module is there, init underscore module is there, which is capital T, which means it is global. And we have hello exit and hello init, which is our init and exit function. These are small t, this means they are static. You can see here the u, it is saying print k is undefined because it's still not loaded into the kernel. Then we have small d, capital D. So static variable is small d. So d small d is a data variable and small d means it is static. So if you can look into manm, so manm. So here it says if lowercase, the symbol is usually local. If uppercase, the symbol is global. And small d and capital D means symbol is in the initialized data section. We have seen U, the symbol is undefined. We have seen T, this means the symbol is in the text section. So you can see here we have global variable, here we have static variable, but we don't have local variable here. You can see we have global, we have static, we have all the functions, global function we don't have static function here. So we don't see a local variable here. You see right? And we don't see here static function. So we don't see the static function and we don't see the local variable present in the nm syntax. So this means those are not being treated as symbols. You can see the static variable, you can see the global variable. So you cannot access, NM cannot provide information about local variables because GCC does not save information about local variables. So local variables are not saved. The information is not saved by GCC. This is because this is why NM does not show anything related to local variables. So kernel provides us a function is calsims underscore lookup underscore name. This function, it takes a name as an argument and it returns the address in memory. So and then calling code can dereference the pointer to make use of that symbol. So it is returning an unsigned long, which is the address in memory. So the calling code, it can dereference the pointer and it can make use of the symbol. If the symbol is not found, the function returns null. So we have seen in our previous example, we have syscall underscore table, sys underscore call underscore table, which is a system call table for 64-bit kernel. So I'm trying to access the address of system call table through my kernel module. So I'm using call sims underscore lookup underscore name. I pass sys underscore call underscore table as an argument. I get the address of the symbol, and I'm printing the address of symbol here, name of the symbol and address of the symbol. So I have made it as module param, so we can use different symbols. We can change the name of this sim underscore name from command line. So let's load this module. So you can see here, it has given us address of symbol of, it has given us the address of symbol. Let me do it again. So it has given us the address of symbol. Let's verify through calsim, actual calsims. So let's search for sys underscore call underscore table. And you can see here the address is the same which we have received when we call the function. It's the same address. So using the calsim function, we can get the address of the symbol, and then we can also call that symbol. We can also call that function, because now we have the address. We can actually call the symbol or function. So dynamical question here is dynamically find the address at which the kernel is loaded. How can I dynamically find the address at which the kernel is loaded? One of the answer is I can use proc IO which has memory map, which displays all the memory map IO mappings, IO mapped IO mappings, and then I can see here the kernel code. This is where the kernel code section is. This is where the kernel data section is. This is where the kernel BSS section is. So here it lists all those sections in proc IO mem. But if I want to find out this through my code, how can I find out? How can I find out the kernel code section? How can I find out the kernel data section, the kernel BSS section from my code? So let's see this. So now we can use calsims underscore lookup name, and then we can specify underscore underscore text, which is a symbol. Underscore underscore text is a symbol. Then we starting of the, which is the starting of the text segment. Then we have underscore underscore e, which is, we have only one underscore e text, which is the end of the text segment, start of the BSS segment, end of the BSS segment, start of the data segment, end of the data segment. So these are the symbols which are exported. These are symbols which are present in the symbol table. Now I can take this symbol and I can convert it into physical address by using underscore underscore PA symbol. So underscore underscore PA symbol will return the physical address of a given symbol. This is giving us a virtual address, right? Calsim's lookup name is giving us a virtual address, but I want a physical address. And proc IO mem is displaying a physical address. So now I can get the virtual address and I can convert it into physical address using underscore underscore PA symbol. So let's verify this. Let's run this code. So if you can see here, we got our text segment. This is all our physical addresses. We got the data segment. We got the BSS section. So this is how we can also verify it. So you can see here, our code was successfully able to match the kernel code displayed by proc IO mem. It was successfully able to, there was some changes. I think we have to find out exact name for the data section. So the end of the data section is correctly being shown, but starting of the data section is not being shown properly. So we still need to find out. So that we can take as an assignment. Then we have BSS segment. you can see BSS starting and ending is same. So through our code, we were dynamically able to find out the start of the kernel code section, the start of the kernel data section, the start of the kernel BSS section. So this is how CalSIMS is very, APIs of CalSIMS are very useful. You can find out all the addresses where everything is loaded. So CalSIMS on each symbol. So this function, it can be used to dump all the kernel symbols along with their addresses. So this function is used to dump all kernel symbols along with addresses. So CalSIMS on each symbol, it takes a function pointer as an argument, and there is one more data void pointer. So function, this is a callback function which is called for each symbol. So the first argument will contain the private data which you want to pass, and which you are passing here will come here. So, and then you have symbolic name here, symbol name, the name of the module, and the address, which address where the module is present. So this is a callback function which will be called for each and every symbol which is present here in the CalSIMS. So this function is used to dump all the kernel symbols along with their addresses. Simple code, very simple code. So I call CalSIMS on each symbol, and this is the function pointer. I do not pass any private data to it. So I have void star data which I do not pass. So I get the symbol name, I get the address at which the symbol is present. So let's load this module now. So this is all, it printed all the symbols you can see here. TMSS now has all the symbols filled with all the symbols which are present now. We gave the symbol name and address. So if you want to dump all the symbols, you can use this. Very low. All the now kernel buffer has been overwritten because a lot of information, and so a lot of print case, so it has overwritten the existing stuff. Now let's try to also add name of the module. Let's try to add the name of the module which is present here. So we have module here. This is a previous code. We are just updating. We want to add the name of the module. So we already have a module which is being added as a parameter to the callback function. And we know there is a name field in the struct module. So we can use that name field and we can print the name of the module. So you can see we have now added the name of the module, and it's printing the name of the module along with the symbol and address now. So which module is exporting which symbol now we have seen, we can see now, we can observe now. So very useful function. So can I find the size of the function? So we are now able to see the functions which are exported. We are able to see the symbols. Suppose if I want to find out the size of the function, yes, it is possible. Okay, using sprint underscore symbol. So this is a function sprint underscore symbol. It accepts buffer which contains which is nothing but the symbol which you want to search, find out, and you need to give the address. So this function, it looks up a kernel symbol. No, you should not give a symbol name here. You have to give address here. So this function, it looks up a kernel symbol with the address, which we can get from CalSIMS again, and stores its name, offset, size, module name to buffer. So you have to give an address. It stores the name, offset, size, module name to buffer. If no symbol was found, it just saves its address as it is. So it does not do anything. It then just writes the address here. So this function, it returns the number of bytes just stored in the buffer. So this is how the buffer will contain. So given an address, it has a symbol name, offset, size, and module name. So if I want to find out the size of print k or offset of print k, I can use directly. I can get the address of print k by using Carl Sims lookup name. I can get the address of symbol. Now I have the address of symbol. I can pass it to. I need to pass a buffer which contains the data. So and then I'll be passing the address. So you can see here we got the address of symbol. Then we have print k. This is the offset and this is the size of print k. So we got the size of print k2 here. So offset plus size. So this is how it works.